My name is Martijn Verburg, and yes, that is a Dutch name. I speak a little bit of Dutch. I was born here, but then I immigrated to the wonderful land of New Zealand when I was 4 years old. So my Dutch is a little bit rusty, one might say. But I still know how to order beer, which is very strange for a 4-year-old to learn. You can blame my parents. Who here has seen me give a talk before? Who here has not? Oh, my sympathies. Well over half of you are in for a really awful journey. So the worst thing about me is that I'm actually not a developer. I am a manager of managers. Boo. So everything I say in this talk is a lie. And for those of you who actually know about this topic, you can inform your colleagues as to what the truth is. But in all seriousness, I have relied on folks within my engineering group at Microsoft to help with some of the technical detail of this talk. All mistakes are mine, all the truths are theirs, and we'll just see how we go. All right, so this talk is going to cover JVM ergonomics as they work inside containers, which is a very exciting topic, I know, but it is actually a very important one, and I'll go into why. And the fact that all of you are sitting in this room tells me that you hate deploying JVMs in containers because it's really hard to do. I'm going to hopefully make your life a little bit worse by telling you some truths. This is what we're going to cover. So we're going to talk a little bit about why JVM ergonomics in containers matters, especially to us at Microsoft. And yes, I'll explain the Microsoft history in a second. Then I'll talk a little bit about the actual JVM ergonomics themselves, plus some hints or some takeaways for you to take back to your day jobs. If you have camera phones or cameras, there's going to be a couple of slides which are really useful. So feel free to snap away when you see those. And we'll also make the slides available later on. In particular, we're going to talk about one of my favorite topics, garbage collectors. How many people here have written their own garbage collector in Java? None. Okay, it's way more fun than you think, really. C in assembly it's the way forward. And then we'll talk about Kubernetes and how horrible it just really is. And you shouldn't use it. You should use Microsoft's Azure Kubernetes service instead. There you go. Did I tell you this was going to be a sales pitch now that I work for Microsoft? Yeah, that's right. All right, so let's talk about Java at Microsoft. Excellent. In all seriousness, so for those who don't know me well, I used to run a small company called JClarity, and I am partly responsible for Adopt OpenJDK, otherwise now known as Adoptium.net. Microsoft obviously found that interesting, and I sold my soul. So I joined Microsoft in 2019, sold my company to them, and started figuring out, okay, what the heck is Microsoft doing with Java? And as it turns out, it relies on Java an incredible amount, as you can see here by this lovely slide. We care about children with Minecraft. Actually, we just destroy their ability to do any schoolwork, but that's beside the point. We help you find your next job with powering LinkedIn with Java. Over 250,000 JVMs runs LinkedIn, by the way. Over 250,000. And we just recently migrated them from Java 8 to Java 11. Every single JVM. Yes, it can be done. Can be done. And it just goes on. So any of you who are running like Apache projects, Kafka, Zookeeper, Flow, I forget all the other names, there's about 20 of them now. They all tend to be JVM based. We run most of them as a service of some description. And so there's millions of those JVMs as well. So we care an awful lot. A lot of that runs in containers, so we care about that as well. So that's the business reason why. And this is the nice saving the planet reason why. So Microsoft, as it turns out, is probably one of the worst electricity users on the planet. We have something like 58 data centers across the world, more than anybody else, I believe. And it's kind of uses as much electricity as probably the entirety of the Netherlands, if not more. It's pretty ridiculous. So we pledged to do something about it. We said we're going to be carbon negative by 2030, which is quite a challenging thing to do when you are a company the size of Microsoft. But when there's a will, there's a way. And so one of the mandates I have from my senior leadership is, hey, you know that Java thing which uses up lots of power? you need to make it stop doing that. Cool. We like big problems, don't we? So running small startup to, make Java not suck up so much power. So one of the really big challenges is that when you deploy JVMs to containers, you waste an awful lot of resources. It's actually astronomically bad. And so that's one target area that I'm looking at internally to go and help fix. There's the motivation. All right, now I'm going to talk a little bit about hardware resources and cloud compute, and I do promise I will actually get to the topic of the talk. I'm just doing some level setting here to begin with, because it's fun. So who here is currently deployed to a public cloud of some sort? Excellent. Who here is on a private cloud internally? Oh, you lucky people. Anyone doesn't care about cloud, just pure hardcore data center, box under their desk? There's usually one. Yes, two in the front row here. Fantastic. I bet you're much happier than the rest of us. I still have a Solaris box under my desk. It's great. Anyway, if you're going to use a cloud, use this one, obviously. Told you I had marketing slides. In all seriousness, you can talk to me afterwards about all the wonderful things we're doing. So data centers. This is actually the picture of one of our Azure data centers. Notice the amount of money we spent on blue lighting. It's very important because it makes it look futuristic. Notice also how tidy the cables are compared to the cables of the two gentlemen in the front here who have computers under their desks. They are wonderful things. If you ever get a chance to visit a data center, you can usually, there's usually programs where you can go see these things. Really go do see one. There's sort of a feat of human engineering that makes you feel like we are arriving in the future. They're amazing things. But the reality is, inside each one of these racks, there are just hundreds, if not thousands, of what we call blades, which is basically something you slot into the rack, which has got some hard disks, some RAM, some networking capacity, and some CPU. If you're into the machine learning or artificial intelligence, it might be a bank of GPUs or NPUs or other specialist chips or devices. Which, as an aside, is some interesting reading for you to all go away and do. The world of we just have CPUs and GPUs, that world is actually already going away. There are now a whole variety of specialist processors, I'll call them, which are designed specifically to tackle certain software engineering tasks like machine learning, image recognition, that sort of thing. So you as software engineers have to start learning more about these new classes of hardware coming in. So there's going to be more reading for you to do. So let's talk about our favorite problem in computer science, abstraction. Whew. So the thing at the bottom is what we call the bare metal. That's that blade I was talking about, right? That thing has got maybe, let's call it 64 gig of RAM, might have an SSD drive in it, might have some networking capacity, and it might have a whole bunch of CPU cores. Great. So instead of running Java on that like we used to, we decide we're going to put an operating system on it, which is typically Linux, yes, even on Azure, a hypervisor, and a hypervisor is the special bit of software that allows you to serve up virtual machines. So when you go to something like AWS or Azure or Google Cloud and you say, I want a virtual machine or several, that's what the hypervisor is giving you. Then you have the operating system inside your VM, right? Again, typically Linux, Windows if you're feeling particularly windowy. In all seriousness, we do still run a lot of server-side Windows. It matters. And then in slightly more, I would call modern-ish clouds, you will have also potentially a container engine running on top of that to serve up all of your Docker containers. And then finally, inside those containers, you're running your JVMs. Can anybody here see the problem? So all the resources that your container is telling you you have is actually a bit of a lie, because the container engine, the guest operating system, the hypervisor, and the host operating system are all taking valuable resource away from the bare metal. So one of the things I just want to warn people about is that when your container is telling you about virtually how much resource it's giving you, just pretend, in fact, don't even pretend, just know it is lying to you. Okay, so when you carefully do your math and say, cool, I know my bare metal thing at the bottom has got, say, 64 gig of RAM. and I'm going to give it 2 containers of 32 gig of RAM each. Those containers don't really get those 32 gig of RAM. They don't get to access all of it, not truly, because the host operating system, the hypervisor, and all these other things need to take a little bit of that first. All right, that's my first little warning to you. So I just talked about all this sort of stuff. What else can we talk about here that's interesting? No, there's a whole bunch of theory. You can go study it up. Then for the lucky of you who are really container pro, you might run on a cloud stack that looks a little bit like this. We get rid of the virtual machines, we get rid of the hypervisor, and we go straight to having a container engine. So the only thing you can deploy is containers. That's all you can do. Can't SSH into a VM, can't do any of those kind of things. Pure container land. So that's becoming increasingly popular. And you'll note, less resource being used. So that's good. We can pack more containers in. That's always good. All right. We talked about that. So I'd like to talk a little bit about basic math. So unfortunately, what lots of public cloud vendors will do, and some of you private cloud people as well, is they will say, haha, we have magic virtualization technology which defeats the laws of physics. And when you have your 64 gig of RAM in your bare metal layer at the bottom, we can magic up 128 gig of RAM instead and deploy that across your containers, because that's how math works. It really isn't. So people may have heard of the term noisy neighbor, and that's what this is generally referring to. Especially in public clouds, if you are not purchasing a dedicated instance, what's typically happening is that you're sitting on a host which is oversubscribed. And the hypervisor and lots of other clever software is busily shuttling resources back and forth to try and keep everybody happy. But if you, like me, we're running a tiny startup and you're sharing all of the same servers as Netflix, your startup would go down every weekend, every evening, every holiday, and it was just impossible to run a business unless you paid that particular cloud provider a lot more money to have a dedicated instance, which made for a very happy cloud provider. So the pro tip here is talk to your SREs or your DevOps people or your system administrators or whatever title they have these days. They'll probably come up with a new one next year. And try and find out what is it we're really sitting on. What's what we call the SKU, the stock keeping unit, and are we oversubscribing on that thing? Because that is going to cause you an enormous amount of problems, and it will make it impossible for you to accurately configure your JVM to run efficiently, because underneath the math just isn't working. So you have to go solve that problem first. All right. Let's talk about some happier news, JVM Ergonomics. And when I say happy, I really mean this. So most of you deploy your application code on your developer desktop or laptop or whatever it might be. If you're using one of our cool new Azure services, you might be doing that on GitHub Codespaces or on Windows 365. Yes, that's a thing. But most of you, despite the promise of containers and Kubernetes, are not deploying to a test environment or a pre-prod environment that matches the same resources as prod. So I'm going to ask that question here. Who here deploys to a test environment which matches their production environment like for like, apples for apples, with resources? 5 of you in the room. But this is what they promised us, right? Kubernetes and Docker containers. We can just spin up whatever we want, and it should be able to match the environment, right? So why are we not doing it? That's a question I want you to go back and ask your bosses and say, why are you not spending the money on Microsoft Azure and helping Martijn's stock price go up and making sure we have these even environments? Because we've been sold this wonderful technology and it does actually work. But if you don't apply it as a business, you lose all the benefits. And one of the biggest benefits you can do is you can spin up what I would call a pre-production environment or a performance production environment. Just spin one up on a temporary basis and load your application into it and do all of your load testing and things before you go to the real production environment. And Kubernetes and containers and all that lovely cloud technology lets you do that really easily, right? From a technology standpoint. Yes, there is a cost involved, but that cost is far lower than dealing with performance problems in production later on. And for those of you who are team leads or managers and things, you hopefully know how to work out the euro cost of those sorts of things. And if you don't, then come and ask me afterwards, and I can tell you exactly how much that stuff costs and how you can convince your boss. All right. So we went out to Twitter and asked a bunch of questions. Because this is how we do customer research in Microsoft. Not really, I promise. And the first question we asked is, how many garbage collectors are available? Right? And the reason why we ask about garbage collectors is because it's the #1 challenge, memory management of Java. It's the #1 challenge that you have when you deploy to containers. Even if you don't think it's a memory problem, it almost always is a memory problem. And I'll explain why. All right, so let's see in this room, who here thinks there are 2 garbage collectors in Java? I've pre-warmed you up with the answer, haven't I? I'll go to the other end. Who thinks there's more than 4? Yes. Who here can name all 7? Nobody. Oh, there's a surprise. We're doing a bad job of actually advertising this stuff. So just for reference, you have the serial collector, the parallel collector, the CMS collector, which is deprecated and going away, so don't use that. You have G1, which is the default for 11 and up. You have Shenandoah, which is the pauseless garbage collector for very large heaps from Red Hat. You have ZGC, which is the pauseless large heap garbage collector from Oracle, and they're kind of competing. I don't know why, but there we have it. Competition is good. You also have this lovely little thing called Epsilon, which is from Alexei Shiplev at Red Hat. Epsilon is very cool because it's a garbage collector that does absolutely nothing. It's a no-op. And we usually use it when us JVM people who actually write code on JVM, we use it for benchmarking purposes and things. But you can also use it in microservices. If you know you're going to have a very short-lived JVM, and you know you just don't need to worry about garbage collecting because that thing is going to die anyway, you can just switch on Epsilon, and you're guaranteed to have no pauses. It's very handy. All right, then we ask some more questions. Do you expect the JVM to do the right thing for you in picking your garbage collector? 3/4 of the people said, yes, we do. 3/4 of people are wrong. Thank you, Twitter. Lovely. All right. And here's the killer. How many of the garbage collectors do you think the JVM selects from when choosing one for you and your container? I'll give you a hint. It's not all 7. It's only 2 of them. And so often, it's picking a garbage collector which is not appropriate for your workload or your container. So that's a problem. All right. Do you trust the JVM to do it? Yes, we believe in Oracle and all the other smart people that work on Java. Do not trust smart people who write books and write JVMs, including me. Not a good idea. Would you like it to be better, though? At this point, the people on Twitter were starting to figure out the leading questions. So yeah, so we got to that. All right. Then we did another survey. It was only 150 people. And we asked, okay, well, how are you deploying Java in containers today? And you can see the numbers there, but basically most people are deploying, between up to 2 gig, some up to 4 gig, and usually 4 gig of RAM. And interestingly, the apps are really I/O intensive. So there's lots of either networking or disk stuff going on. Disk stuff in Docker containers is bad, by the way. You should really stop doing that. All right. So then we asked our friends at New Relic, who have over 10 million JVMs that they monitor. And we asked them, okay, what's the ecosystem really doing? And these results are skewed by New Relic customers who tend to be more of the greenfield microservices. We have built a relatively new Java app, just to be very clear here. So the results are skewed. A majority of these people, including most of you in this room, I think, are deploying with only 1 CPU in your container and only with 1 gig or less of RAM. Who here thinks Java was designed to run in those small resource environments? One person, one very brave person. It was originally, to be fair, back in the early days of Java, because it was meant to be for network computers and smart cards and those sorts of things. But over time, it grew with the industry, and Java was really designed for running on big iron, as we used to call it. So what do? When the thing doesn't work in the cloud, we go 1 gig of RAM wasn't enough, we'll double it to 2. that's not enough, we'll double it to 4. Oh, we'll double it to 8. And the cloud vendors say, thank you very much for spending all of that money on us. Wonderful. So this is bad. And I can speak honestly from Microsoft's point of view as well. We don't want people unnecessarily paying for cloud resource they don't need to use. We would rather that you actually run an efficient workload and you trust us to run that workload for much longer in life. All right. I'll now talk about the JVM ergonomics. So, who here is on Java 8? Okay, you can all leave the room now. Because first of all, you should be ashamed. Second, I'm mostly going to talk about Java 11 and up. So only some of the stuff will be applicable. As I mentioned previously, we strongly believe in modern Java at Microsoft. We've managed to migrate almost every service to at least 11. We've got Minecraft to 17. And I will tell you the business benefits of it that you can convince your bosses with are just overwhelmingly positive. The costs, what we call costs of goods sold, the amount of money it takes to run your Java in terms of hardware and memory and CPU and all that sort of stuff, will decrease dramatically as you go from 8 to 11 and then 11 to 17. Developer productivity. You'll actually have developers who love writing Java again and they won't resign and go become JavaScript developers or Go developers, right? Lots of reasons, and again, I can talk to some of the dollars and cents. You'll also get increased throughput, so you'll be able to execute more business transactions per second if that's something you care about. And your latency will get better as well, in terms of you won't have as many of these pause events happening, so your application will just become more performant. So please do convince yourself and your bosses to get off 8 as quickly as possible. Right, that's my little lecture over. So if you're Java 11 or later, you only get to select from 2, or the JVM will select for you, between 2 collectors. The very venerable and old and still quite wonderful serial GC, that was Java's first garbage collector, basically, or G1 GC, which is now the default. What else do I need to say here? Right, yes, there's a key bit that I'm hiding there at the bottom. G1 GC will only be selected as a default if the JVM thinks you have 2 or more processors and more than 1,792 meg of RAM, because we like random numbers. Don't ask me why we have that number. And remember, in the previous New Relic slide, most of you are running with only 1 CPU and 1 gig of RAM or less. So what's the collector you're going to get by default? Serial, that's right. Does anyone know what the worst thing about the serial collector is? It's serial, yeah. The worst thing about it is that it has got some pretty nasty what we call stop the world characteristics. So when it decides to go do a garbage collection, it says, nope, JVM, you're not doing any other work. I'm going to bring all of your application threads to a screaming halt. We call that getting your threads to a safe point. Then I'll do some garbage collection. Your users will be on the phone yelling at you because your application sucks, even though you're in this cool new cloud, and everybody is unhappy. So not necessarily the best choice. Let's see. That's warning number 1. Another small warning that I just had to insert here is that if any of you are using Docker containers with the cgroups v2, which you should all be doing, because you're all modern Docker container people, Java 11 is kind of broken on it, which is why you should have migrated to Java 17 in the first place. Just saying. All right. So now I'm going to try and do a little bit of a demo. And because I'm a manager, I've decided to use GitHub's Copilot AI to write the code for me, which I'll try and show. I'm going to use VS Code because I just do code editing, not real software development for Java. And I'll see what else breaks along the way. So let me see here. I also need to start my Docker daemon. So let me just start Docker first, because that always helps. And on a Mac, that will only take about 5 minutes to start. But in the meantime, I'm going to use, let me see, I'm on the right screen here. Right. So this is this great website called Hackertyper, where basically if you just bash in on the keyboard and you're sitting at a cafe, people think you're a really cool programmer. So as a manager, I find this pretty darn helpful. So after I've written some code, that's good, I then swap to Visual Studio Code. Who here uses Visual Studio Code? Because it's awesome. So in all seriousness, I use this for all of my lightweight code editing and when I'm doing like little microservice-y type stuff, when my engineers let me touch code, which is never. When I do serious Java development, which is on the very odd occasion, I still use IntelliJ's IDE, which is a brilliant IDE, of course. So what I want to do is I want to find out how many processes my container thinks it has, or my environment thinks it has. So, because I'm running Java 17, Microsoft build of OpenJDK, by the way, Java 17, we do have one of those. I can use the cool var keyword, and I can say processes equals, let's go runtime. Can I type while looking at the screen down there? Dot get runtime. Oh, look, thanks, Copilot. Nice. So Copilot discovered, oh, look, this is Copilot again. So this is GitHub's AI going, I think I know what you want to do next. You just want to do that. And it's correct. Cool. So GitHub Copilot is coming out. No, stop trying to write formal code for me. Stop it. So the only issue I have with GitHub Copilot is that I think we're all going to be out of a job in 2035. But I do find it very handy for writing code, especially in languages that I don't know. I even managed to write like 100 lines of Rust the other day. It was really fun. Don't know what any of it does. So I run that. And you can see there, it's a little bit hard to see, so I'll try and highlight it. My aging MacBook Pro here has 16 available processes. And what I would challenge you is to find out how many available processes your JVM thinks it has in the container. And you can use this tiny snippet of code if you can't read YAML or Docker files or figure it out in any other way. You can just run this tiny bit of Java code for it to tell you. If you are running an old version of Java 8, anything that's older than 1.8_292, it gets this wrong, which is even worse, right? So for people who are running old versions of Java 8, if you're running in containers, the JVM can't figure it out at all. It's a bit stupid. So you need to be on the very latest version of Java 8 if you're going to be doing this stuff. So that'll help you figure out how many containers. Then I will swap to, let's have a look at this other thing you can use. So the other thing I want you to learn is figuring out what garbage collector the JVM has chosen for you as a default. So if you don't select your own, which you always should, but if you want to find out what it has selected for you, you can do something like this. So I'm using Docker because we're talking about containers. I have 2 CPUs. I'm going to limit it to 2 CPUs. And note there I'm limiting the memory to 1,500 meg of RAM. Can everyone remember that special number we looked at before? Yeah? Okay, good. Keep that in your heads. I'm going to the Microsoft Container Registry because I don't trust Docker Hub. Nobody should trust Docker Hub anymore. And of course, I'm pulling down our build of OpenJDK. I'm using this really cool flag called print flags final. That shows you all of the hidden flags that the JVM actually starts up with. There's about 600 of them, so you have to use grep to filter through them. But if you want to find out all of the defaults that are actually happening and learn about the other 600 flags, because we have way too many, you can do that. And then I use grep because I'm command line pro, and I'm going to try and figure out what garbage collector we're using. Cool. Then I'm going to swap to this cool command line here. I'm going to run Docker, and it's going to magically work. Yes. All right. So you can see the line there which says true. Okay. Whoops. Come on, highlight. There we go. And it's using the serial GC. And the reason why it did that is because it was less than 1,792 meg of RAM. So instead of selecting the G1 collector by default, because I'm running Java 17, it decided to pick serial instead. Okay. So that's something that you can also try and figure out in your Docker containers as well. So that should help you. Now Docker's yelling at me for running stuff as root. Whoops. You should never do that either. All right. Back to the presentation. So there's an example of the code I wrote. Docker stuff, use serial GC. All good. Let's now talk about the collectors. So instead of letting the JVM select the collector for you, you need to set it yourself. So you have to get into the habit of explicitly setting your GC. We have given you some guidance here. This is one of these moments where you can go take a photo of what we have seen when we've analyzed our 2 million JVMs plus JVMs running lots of different workloads. If you genuinely only have one core and you have a really small heap, then serial is actually really good. And the reason why it's good is what we call a high throughput collector. It allows you to whip through lots more business transactions per second, I'll put it that way. And then you just take the little stop the world pause every time. But if it's a small heap, that stop the world pause will only be of a small amount of milliseconds, and users can usually survive that. Then as you go along to the right, you want to select the appropriate garbage collector until you get to these really large heap ones at the end, ZGC and Shenandoah. That's for people who run heap sizes 64 gig plus. We've seen terabyte size heaps. Yes, Java can actually do that now. If you're on Java 11, your only choice is Shenandoah because ZGC is experimental in Java 11. They're actually not going to complete the work there. And your JVM will just blow up at some really, really bad time. Like when you're running a nuclear power station or something, which is not good. All right, so those are all of your realistic choices. I also spoke about epsilon briefly. That's the extreme case. And if any of you are using CMS today, that was deprecated in 11. It's been removed in 17, so you will need to choose something else. Alrighty. Because I work for Microsoft, I get paid by how many bullets I put in a PowerPoint slide, which is why there's so many here. So the thing you really want to focus on is the thing on the bottom right-hand side there. You can't just set -XMX anymore, or set your max RAM percentage. You actually have to understand what type of workload you have, how many CPUs you have, and all those other good things. And I gave you some tools earlier on how you can go find those numbers out. Some other fun things about heap size configuration. If you don't manually configure the heap, and you always should, in containers especially, if you don't, you'll only get a quarter of the container memory. Okay? And if you're on an actual server, most of you remember you only get 1/64th of the memory, which is just tiny and almost useless. So instead, what we tend to recommend is if you know exactly what your workload is doing and it's really stable, so you think things like a Hazelcast cache or something along those lines, something that you know is just going to be stable for a very long time. You can still use good old -XMX and that will work well for you. Otherwise, the bottom one is the one you want to use in containers. And you typically want to start it at about 75%. So your heap will start with 75% of the memory that your container says it has available. And the reason we say 75, it's just a rule of thumb, is because you need to give the container enough native memory space for it to do the rest of the stuff it needs to do, which could be the bits of the operating system that are running in your container, things like gRPC, things like the JVM using off-heap memory, which it does for things like code cache, or if you're using things like Netty, for example, or if you're using things like Apache Kafka or one of the other big data products, they tend to store a lot of data off heap. So 75% is a rule of thumb, and the larger your container goes, the higher your percentage can also typically go. But I'll reinforce this message. The critical thing is to understand if you're using a framework or a library that has lots of what we call off-heap memory, like it stores stuff in native memory, you need to try and measure that. And I forgot to put it in these slides because I'm evil. But there is a special flag called --XX native memory tracking, I believe it's called. And you can add that to your JVM and it will tell you how much native memory it is creating, which is very helpful. And you can then look at the native memory and the appropriate debugging tools to find out what that all is. All right. Covered that. I think this is just me repeating what I said before. So we'll carry on. All right, let's talk about Kubernetes. Who here is using Kubernetes of some description? Keep your hand up if you enjoy it. A few of you do. Insane. So I will make a nod to Oleg's talk earlier about test containers. If you missed his test containers talk, I highly recommend you find a video or find his slides. It will transform your life because you won't need to write YAML anymore. And we all hate writing YAML, I hope, except for the sadists in the room, potentially. All right. So I was going to do a demo on Kubernetes, and then I looked at all of the basic Kubernetes commands, and I went, I don't have 2 years to learn Kubernetes. Then I went and researched what Kubernetes really means, and I found out it's a very rude word in Klingon. And I said that rude word live at another conference and nearly got fired, so I'm not doing that here. So then I decided to do this instead, to learn about Kubernetes. And unsurprisingly, it worked, because that's how we all drive our careers forward. And this is what I learned. Kubernetes doesn't really have this concept of a CPU core or a virtual CPU. It has the concept of time spent during a CPU cycle. It gives you time slices of CPUs. Now, the JVM doesn't understand this natively at all. Right? This is one of the big challenges that Java has today, and it will get resolved in a future version of Java, and it'll get backported to something, but not Java 8. So again, please move off Java 8. And it basically, in Kubernetes, you basically say how much millicores of time slice am I going to give the pod. And you may remember that Java applications are multi-threaded. And so you have all of these interesting little Java threads doing things which will use up time in your time slice that are not your business threads doing business work. And so one of the things that always happens after I give this talk is that everyone goes away and goes back and has a look at their Kubernetes throttling stats in their cloud, and they realize they've been running their apps at about half speed for the past 2 years. And they're very embarrassed, and they never tell their boss because it cost a lot of money. We'll give a little example of how this works. All right, so we're given it a CPU limit of 1,000 millicores, and that is roughly equivalent to 1 CPU. So if you remember, most of you were running containers with 1 gig of RAM or less and 1 CPU. Yeah? So most people, when they move to Kubernetes, they go, aha, we will do the same thing. 1 core is about 1,000 millicores. Perfect. We'll use the same number. All right. So some HTTP requests come in, and they go back out. And each of those took 200 milliseconds to do. So 200 times 4 is 800, so we have 200 left. And by the way, if you think that I'm really good at making slides like this because I'm a manager, that's not true. I have PMs or product managers who are really good at making slides like this. So you have to thank Bruno Borges on Twitter for making this wonderful slide with animations. So I'd have no idea. Then some garbage collecting comes in, and takes up some time. Takes up the remaining 200 milliseconds, which leaves us with 0 CPU time left for this cycle. Some more HTTP requests come in. We're not allowed to. We're being throttled. Bonk. Doesn't go through. And then what you have to do is you have to wait until the completely fair scheduler, which is the most awesomely, confidently named piece of software in the Linux kernel. Kudos to the engineer for doing that name. You have to wait until it ticks around again before you are allowed to have another go. But the problem just keeps propagating itself, right? And so quite often you'll see lots of these Kubernetes-style applications being throttled. In this particular case for 60 milliseconds, because that's where the period was set to. And yeah, so an awful lot of wasted stuff happening. Now I mentioned before that as far as the JVM is concerned, it doesn't understand millicores natively. So it converts everything to what it knows, which is processors. And up to 1,000 millicores, it goes, yep, that's one processor. Between 1,000 and 2,000, 2 processors, so on and so forth. Pretty simple. The challenge, of course, is if you are using a garbage collector like G1GC, which is constantly using threads to do its cleanup as it goes, right? That's a problem when the JVM thinks it's only got one processor and only one thread to work on. So you have to lie to it. You have to say, no, JVM, you are not working with a real processor. You're working with magic Kubernetes millicores. And that might be spread over multiple processors, so you're actually OK. So what you do is you use that flag there, the active processor count, and you tell the JVM that you have at least 2 processors if you're using the G1 garbage collector. In fact, just in general, you probably want to tell the JVM it's got at least 2 processors no matter what, because Java is just used to needing lots of threads, and it expects to have more processors available to it. And it's reasonably safe to do, because remember, Kubernetes will distribute all of the threads across lots of real cores, because it's time slicing. All right, so I'll stop here and let people take photos. This is guidance. We call it pirate guidelines because this is not a hard guideline. Okay? You need to check whether this will work for your workload and your situation. But as a general rule across lots and lots and lots of JVMs that we've studied at Microsoft, we think these are pretty good starting points if you don't know where to start. And there's a couple of key things. Remember, if you're using 1,000 millicores or less, you should always set your active processor count to at least 2 to trick the JVM into thinking it's got more CPUs. Yeah, that's really important. Your container size should be set to about your heap size should be set to about 75% of your container size, and you can increase that number as the container size goes up to much larger numbers. But please, please take care to make sure you understand off-heap memory usage. It's really important. And there's some guidance there on which garbage collector you should choose as you walk through the size of your heap. All right, I think everyone's taken their photo, so I'll carry on. I'm going to skip past this slide because I've got no idea what it means anymore. And I'm going to talk a little bit, 5 minutes left, perfect, about the cost implications as well of deploying to cloud and Kubernetes and containers. So here you have an example of where people have gone, we're going to scale out horizontally, we're going to go across. And we have packed in more VMs, and we're packing in more containers into each of those VMs. So you can see here the total resources consumed is 18 JVMs, 18 virtual CPUs, and 36 gig of RAM to do all of this work. Okay, there's a cost there of $840. We told you Azure was good value for money. And note, however, that the default garbage collector that's going to be chosen here is going to be the serial GC because every JVM is starting with only 1 virtual CPU. Okay, you remember you have to have 2 for the G1 collector to kick in. So all of these JVMs are going to be running that nasty little stop the world collector on a 2 gig heap size, which is actually significantly sized enough that you're really going to see the impact when that thing does stop. Alternatively, you can run exactly the same service, exactly the same application, but just package it differently. You can go narrow and tall instead, because this is actually what the JVM is still really designed to do. You'll note here the cost is exactly the same. So it doesn't cost you any different to do it this way, which is very, very helpful. All of a sudden, we've reduced the number of virtual CPUs we're using by 6. We've reduced the amount of RAM we're using by 12 gig. We're using a better garbage collector for the size heaps that we have. So you're getting better throughput, better latency, it costs the same, you're using only about 2/3 of the resources. All of a sudden, everybody is much, much happier. So when you're talking to your SREs and your DevOps people, they may not understand this about Java, right? They're just used to deploying a container and whatever runs in the container. You can help them understand that Java typically wants to go narrow and tall, as opposed to short and wide. Hopefully that all made sense. Skip past that. All right, we're getting to the end. So, to reiterate, you need to understand your tech stack right from the bare metal at the bottom, right? Understand that stock keeping unit you have and whether you're oversubscribing your container resources. You want to understand some of those JVM ergonomics, and you saw some tools on to help you find those numbers. As boring as it sounds, you have to understand Java garbage collectors at least to a little bit. And if you do, you sound really professional, and it's great for your next job interview. Not that I'm encouraging you to leave your jobs. We're hiring, by the way. You can then monitor and look at the numbers, because we always say measure, don't guess, right? And there's a bunch of free tools you can use out there. including being able to analyze Java flight recorder data, or the JDK flight recorder data. We have a free streaming library. Just go to github.com/Microsoft and you'll see a JFR streaming library. We also have one called GC Toolkit, which allows you to read garbage collection logs so you can understand what your memory management is doing. All right, so in conclusion, depending on your workload, you may need to have a different topology, right? So remember, you might need to go narrow and tall versus short and wide. It really depends. JVMs still like to have more resources than you think. You can't just pack them down to these tiny little, 256 meg of RAM, 500 millicore type Kubernetes clusters. In a lot of cases, if you really know what you're doing, you can, but Java just still isn't quite designed that way. Avoid the JVM default ergonomics. Always set explicitly your heap size, your garbage collector, and the number of active processes that you have. Don't leave it up to chance. And then, as I said, analyze the data after a run, right? Use JFR or GC logs, whatever you might need to use. If you want the deep dive detail, you can look at the second edition of the Well-Grounded Java Developer, which is coming out, I believe it has actually been released. Jason Clark, who works for New Relic, he wrote the chapter on containers and JVM ergonomics, and there's about 30 pages of proper deep dive technical information on this topic, if you really want to learn it. The second link there is, and everyone feel free to take photos, is basically this presentation, but in documentation format that you can share with your colleagues. And, oops, some people want to take a photo of that. I'll go back. Why I wrote out these full URLs, I don't know. I could have used a URL shortener. But I'm evil. All right. And lastly, we would love for you to follow our adventures at Java at Microsoft. That's where we tend to post some of our interesting technical content. And we have a lot of fun. It's low traffic, so you're not going to get spammed with lots of, hey, come run your Java on Azure, it's great. There's a separate marketing Twitter handle for that, so we let them do that. So actual technical content will come out of there. And if you do want to start your journey with us and understand what we're doing with Java, including LinkedIn, Minecraft, all these cool things, then docs.microsoft.com/Java is our portal page for everything we do. Thank you very much for listening. I hope you found it useful, and I think I've got time for questions because it's the last talk of the day.